This conference will now be recorded.
Thanks. Okay, Andrew, are you okay for me to start?
I am, yes. Thanks, Tracy.
Okay, cool. Okay, hi everybody. Thanks for joining us for this webinar today. I'm Tracy Drew. I work at SRK, and I'm also the chairperson of NICOLA, which is the Network for Industrially Contaminated Land in Africa. We have a jam-packed session today, so I'm going to jump straight in before I hand over to our guest speaker, Andrew, in a moment. Okay, so we at NICOLA are all focused currently on SUSTREM. We made the decision to go virtual. Predicting the future was very difficult, and we have been thrown a few curveballs. But finally, we're 2 weeks away, and we're very much looking forward to the conference. If you haven't registered, I'm just going to give a little overview. It is the 6th International SUSTREM Conference. They have been held in Denmark, Austria, Italy, Canada, and Brazil, the last one being Brazil in 2018. Historically, the conference actually takes place every second year, and NICOLA won the bid to host SUSTREM 2020 in Cape Town, South Africa. But COVID had other plans, and we are now hosting the conference in 2021 virtually. The main conference will be on the 4th and the 5th of November, and if you haven't registered, Rochelle, can I just ask you to drop the link to the registration in the chat now? Also, all the details are there, and the draft program is available on the website. And if you're lost, please contact myself or Rochelle or any of the steering committee. We'd be very happy to help. Okay, then I thought I'd go over a little bit of the warm-up events. We have NICOLA, in collaboration with NICOLA-Latin America, will be delivering a sustainable remediation workshop focused on stakeholder sites, and that will take place on the 3rd of November. The workshop is aimed at experienced professionals. We're also holding a Kickstarter program, and we're very happy to announce that this has been well received, and we have capacity for both mentors and mentees. And finally, on the 3rd, we are Claire and Surf UK are delivering a sustainable remediation training course as part of SUSTREM. The training will also take place on the 3rd and is aimed at entry-level or early year professionals. All the details are on our website, but please contact myself or Rochelle and we can point you in the right direction. I'm just going to play a little video you might have seen on LinkedIn. Again, Rochelle can drop the link so that you can watch it at your own time. And if you can, please, can you share it far and wide? We would love that.
Hi, I'm François Baudouin.
My name is Anna Moeri.
I'm Klaus Weber.
My name is Claudio Albano.
Hi, I'm Tracy Drew.
My name is Linda Wissler-Marne, and I'm a member of the NICOLA Steering Committee.
SUSTREM 18 brought a lot of change to the ECOS Brazil seminar. It was part of a strategy to explore these new and innovative solutions in Brazil.
The discussion sessions in particular we held made me realize how important these types of events are. They allow you to expose yourself to different points of view and really change your perspective on things.
The Sustainable Remediation Conference was a great event attended by hundreds of professionals. The discussion focused around projects, technologies, and sustainable remediation appraisal tools. And we also had great fun.
The idea of an international green remediation conference was born up to the COP15 conference that were held in Copenhagen. We didn't know that this should be the first of a series of conferences. You can thank passionate people, of which I can see several are also part of the upcoming conference in South Africa.
SUSTREM 2021 will be the 6th International Sustainable Remediation Conference and will be held virtually for the first time ever. Hosted by NICOLA on the 4th and the 5th of November 2021.
So join us.
Come join us
at SUSTREM 2021.
I hope to see you there.
Okay. Thanks for that. Okay, then I just wanted to quickly let you know that as part of SUSTREM, we are going to be sponsoring a Trees for All event And we're going to be planting 90 trees at 3 different locations in Cape Town, Durban, and Pretoria on the 25th, 26th, and 27th of October. A tree will be planted on behalf of each delegate, and the delegates will receive an e-certificate after the conference. Please contact us if you are interested in joining us for the event planned in your region. Okay, then we have some exciting news. The Memorandum of Understanding between the DFFE and NICOLA was signed, and this is to formalize and promote our working relationships, and we're super excited about this step. So thanks to that. And then we also have the Memorandum of Incorporation has been compiled and finalized. We will require acceptance, of course, of the MOI by the members during the AGM in November. Once this happens, these documents will replace the NICOLA Constitution. Okay, and on the AGM, we are going to be holding an AGM on the 24th of November. The AGM will also be virtual, and we are going to have a webinar in conjunction with the AGM. Please watch out for the invitation for that. Okay, now the reason you're here. I'd like to welcome Andrew Gemmell. He's a registered professional natural scientist and has an MSc in hydrology. Andrew has been an environmental consultant for 12 years and has experience in surface water, groundwater, soil, contaminated land, and other related projects, which include oil and gas, mining, manufacture, chemical power, transport, and commercial sectors. Andrew is currently employed by Groundwater Africa, a water resources development and management consultancy. And from 2019 to 2021, Andrew worked as an affiliate consultant for the United Nations Environment Programme. And he was under the supervision of the head of Global Environment Monitoring Systems for Freshwater. Andrew coordinated activities related to the World Water Quality Assessment Pilot Use Case Approach in Africa and related water quality activities focused on Lake Victoria and the Volta River basins. Thank you very much, Andrew, and I'm going to hand over to you.
Thanks, Tracy. So as Tracy mentioned, I will be speaking around the groundwater numerical modeling of the Cape Flats aquifer. I would like to welcome everyone to this lunchtime brown bag, and thank you to NICOLA for this opportunity to present. As Tracy said, I represent Umboto. We're a water resource development and management consultancy based in Cape Town. Specifically on the topic, I'll be presenting on the Cape Flats aquifer, as well as the numerical modeling undertaken towards the protection of this strategic water resource for the city of Cape Town. The presentation comprises 10 information slides, so relatively short, but I will be providing quite a bit of detail for each of those slides. And then at the end, there will be time for any questions. And I do see some of my colleagues are on the call, so they will be able to step in for any questions that I don't have the answers for, hopefully. So the Cape Flats aquifer, it has the acronym CFA, and that's represented, or the boundary of the aquifer is represented by the blue outline in the figure. It's an unconfined sand aquifer located between Table Bay to the north and False Bay to the south, and underlying the Cape Flats area of Cape Town, hence the name. The Cape Flats aquifer is a very important water source for irrigation in the Philippine horticultural area, otherwise called the PHA, which is shown in the green outline in the figure. And this supplies vegetables to the city, as well as an important hub for employment in communities within Cape Town. In addition, the city of Cape Town develops the Cape Flats aquifer to supply groundwater for potable use to the city. The location of the planned production well fields are outlined in red. And this was all driven by Day Zero, which happened a few years back, and the city's plans towards solutions to avoid the similar recurrence in the future. So This slide gives a lot more detail on the geology, so I'll talk you through it. The figure shows the Cape Flats aquifer boundary. That's a black dotted outline which you can see, as well as rivers shown by the light blue lines, the various geologies encountered, as well as the registered groundwater users shown in red crosses. And you can see quite a dominance of those within the Philippi horticultural area. Then I've also included a cross-section taken at the red line in the map you see there, taken from a west to east, with a cross-section representing that transect. You can see in that image the cross-section of the unconfined sand aquifer, which consists of fluvial, marine, and aeolian, tertiary, and quaternary sedimentary deposits of the Sandveld group, above a basement comprising of the Malmesbury group and Cape Granite Suite. So what we've noticed through the drilling works that we've undertaken is that those sands contain, in some areas, layers of calcrete, and in other areas, layers of peat. And in addition to that, you can see in the cross-section in the orange, gravels and shells, which are representative of a paleo channel, interpreted as a diverted riverbed that contains gravels and shells, which really acts as a preferential groundwater pathway that directs the groundwater towards False Bay. So this slide gives a little bit more of the conceptual sketches indicating the proposed change from what is the current Cape Flats aquifer water cycle, and by extension the city's water cycle, to the proposed future water cycle for the city. Currently stormwater and treated effluent together is released to False Bay with very limited recharge of the aquifer, which results in a loss of this very important water source for the water scarce the city of Cape Town. So because of this, the planned future water cycle includes the following three main interventions. There's going to be managed injection of secondary effluent or treated secondary effluent to artificially recharge the aquifer, thereby maximizing storage and improving water quality of the aquifer. Typically, the recharged water of treated effluent will be of a better quality than the existing groundwater, thereby improving the quality. There will also be the rehabilitation of damaged wetlands in this urban environment, the development of artificial wetlands, as well as the development of stormwater infiltration basins to recharge the groundwater. The wetlands will also provide an added benefit of acting as a polishing step to improve water quality, recharging the groundwater. The abstraction of groundwater will then occur from these production boreholes from various well fields, and this water will be treated to a potable quality for supply as a potable supply to the city of Cape Town. And I guess allied to that is the real need to improve the quality of living of residents within, especially informal settlements within the city of Cape Town, and specifically on the Cape Flats aquifer, through improved water and sanitation supply, which hand in hand reduces the sources of impact to the groundwater by formalizing sanitation, as well as greening of the informal settlements. And that really ties up what the city is planning for the Cape Flats aquifer. But what's notable is that due to the unconfined primary sand nature and high infiltration rates of the Cape Flats aquifer, it's highly vulnerable to pollution from land use activities. Because of this, a groundwater protection scheme needed to be developed to protect this vulnerable groundwater supply and strategic supply to the city. In addition, potentially contaminating activities that are proposed at the Cape Flats aquifer or in the vicinity of it needed to be understood to ensure the risk is appropriately understood as well as managed. So in the coming few slides, I'll be providing more detail on these activities undertaken by Mvoto, both in terms of the groundwater protection, as well as a couple of examples of what needed to be done to manage these potentially contaminating activities. So this slide gives the an overview of a few things that map shows the groundwater protection zones. In terms of pollution sources, there's various pollution sources within the Cape Flats Aquifer, and this includes informal settlements, industrial land use, unlined cemeteries, underground fuel tanks at filling stations, landfills, surface water features including canals, sand mines, and wastewater treatment works. So because of this, a groundwater protection scheme was developed to ensure the protection of the groundwater quality. The protection scheme was comprised of several components. The first was the development of groundwater protection zones. The second was vulnerability mapping and ranking. This was done using a drastic model specified vulnerability index. I won't go into too much detail on that for time. The third was identifying potentially contaminating activities within the Cape Flats Aquifer, and then identifying associated remediation plans for each of those contaminating activities. So the vulnerability mapping indicated a very high to extremely high vulnerability of the aquifer to pollution sources on the surface. So to reduce the risk of pollution entering the proposed abstraction boreholes for water supply, which in that figure is represented by black dots, protection zones limiting certain land uses were proposed, depending on the expected residence time of pollutants entering the aquifer. And that was modeled as a lifetime expectancy. So in essence, zones 1 to 5 were developed. Zone 1 to 3 are shown in that image as purple to teal shading. And those areas really needed strict restrictions on land use. So more specifically, zone 1, which actually won't be visible in that image, was a 10-meter radius around the wellhead itself. And that was really to prevent the rapid ingress of any contaminants. There were strict rules around that area where no activities of any sorts are allowed, and the land must be routinely cleared and kept clean of any potential contaminants. Zone 2 was a 2-year travel time. The literature notes that pathogens and bacteria cannot survive in groundwater for more than around 2 years. So this is what was used to define Zone 2. Zone 3 was a 5-year travel time. This zone provides an adequate amount of time to respond to possible chemical spills. So within 5 years, spills would be identified and be able to be managed in a way that limits the impacts to production wells. Zone 4 was a 5 to 10-year travel time of any groundwater pollutants, and that provides adequate amount of time to respond to any chemical spills of more persistent chemicals. And then lastly, Zone 5 was a full groundwater catchment area delineation, which is beyond the 10-year travel time. Obviously, with the travel times, we needed to calculate that. So we used the numerical modeling program FeeFlow to calculate the travel times for each of these zones. And that was based on our existing model that took into account the entire Cape Flats Aquifer. And the final groundwater protection zones for the CFA management scheme was defined by a combination of the various abstraction scenarios planned by the city. That includes the Philippi horticultural area, as well as the various stages of abstraction of the groundwater for the city. So this slide shows where the 2 stars are in that image. The 2 examples of modeling work that was undertaken by Unvoted to really assess the potential of pollution sources impacting the receptors. And I will give a bit more detail on those 2 examples in the coming few slides. So the first example was a proposed service station. This service station was underlain by the Cape Flats Aquifer itself and was located near the proposed production and managed aquifer recharge well fields, as well as close to the sensitive Philippi horticultural area. There were concerns around a potential for any leaks or spills from such a site contaminating the abstracted groundwater, both by the city as well as the farmers, and the relative timeframes in which these would be likely to occur. So to assess these concerns, the flow paths and timeframes of contaminant transport in the groundwater were determined using a subsection of the existing aquifer scale model, which had been developed by Envoto. And this sub-model was used to simulate transport processes of a hypothetical spill or leak in the service station under current conditions, which included the abstraction for irrigation in the agricultural area, as well as for future scenarios, which included the City of Cape Town's planned groundwater abstraction, as well as their managed aquifer recharge. As an indicator, methyl tert butyl ether, everyone knows it as MTBE, was used in the modeling, as it tends to be more mobile in the subsurface than most other fuel components, and was used as a constituent as a conservative compound that may contaminate the groundwater. Predictive simulations were run over a period of 10 years, and that was assuming a constant source of contamination. Only non-reactive additive dispersive transport was simulated, and no account was made of processes in the unsaturated Vado zone. This was a conservative approach. It ignored any biodegradation or retention by absorption, which may occur in practice, which would then limit the extent of contaminant travel. This was done, as I mentioned, as a conservative approach. So despite biodegradation or retention being excluded, we still used MTBE for indicative purposes for future modeling scenarios where one could then include chemical specific data to give a more realistic indication of these biodegradation or absorption processes in the aquifer. So what do the outcomes look like? The predictive simulations are shown, and what that showed was that should contamination reach the water table, agricultural groundwater users in the vicinity of the service station could be affected within a period of around 50 to 120 days. And that was from a time of groundwater being impacted by the contamination. This is shown in the figure to the left, with the agricultural irrigation boreholes shown as green dots. And they act to draw the plume towards them due to quite high levels of abstraction. On the other hand, on the right-hand side are the city's planned potable water supply well fields, which are only likely to be affected in very extreme scenarios after several years of continuous contamination. In practice, monitoring and contingency plans at any of these fuel sites, as is legislated, would be expected to identify and remediate contamination before it affects other users. So what you can see is the abstraction boreholes as the red dots and the injection boreholes as the blue dots, the light blue dots. And what it shows is that despite ongoing abstraction from the PHA and abstraction from the production boreholes in red, the injection wells would act to limit the westward migration of this hypothetical plume in the case of the Cape Town scheme put in place. So the second of the examples is where modeling was undertaken to identify how a contamination plume from a hypothetical unlined wastewater treatment works sludge ponds could migrate under current and planned operating conditions. The relative influence of several operational and mitigation options were also explored. Again, the modeling results were based on the calibrated Cape Flats aquifer model developed by Envoto. Under the planned operating conditions, as groundwater is abstracted from the production well fields shown as the red dots, there is expected to be a reversed or an inland flow direction. And it's for this reason that a saltwater intrusion barrier is visible towards the ocean as the blue dots to limit any intrusion of saltwater into the aquifer. And then given the expected migration of the identified groundwater contamination from the area of the wastewater treatment works towards the abstraction well field, rehabilitation measures needed to be proposed to limit the impacts of these important abstraction zones. And that's shown in the in this slide here, where the proposed rehabilitation measures included the following steps displayed visually in the figures. The first step for this hypothetical sludge ponds associated with the wastewater treatment works would be to capture the pollution plume that would be occurring within the aquifer using capture boreholes. That would abstract any impacted water, and this would be sent to the wastewater treatment works for treatment. The second step would be the removal of the contamination source associated with the sludge ponds through excavation of the material. Thirdly, excavations would be refilled with clean soils, leaving shallow depressions to enable rainwater infiltration to promote the vertical migration of any residual soil beta zone impacts into the groundwater. The fourth step would then be the modification of the groundwater flow pathway by implementing the managed aquifer recharge scheme by the city that acts as a hydraulic barrier to prevent a link between the contaminant source and any receptors. And then the last step would be ongoing treatment of any residual impacts in the groundwater by ongoing abstraction of the groundwater, shown in that final image. The results of this is shown in this image, or these images, where image 1 on the left shows the contamination plume from the sludge ponds spreading inland once the production well field abstraction, shown as red dots by the city, commences. Image 2 shows the effects of the designed capture, red dots and recharge barriers, blue dots, immediately surrounding these sludge ponds. And really what would happen is that the planned mitigation measures would avoid further spreading inland to these abstraction well fields. So after these examples, in summary, taking into account the groundwater protection scheme, which I outlined, as well as the 2 examples of the fuel site and the hypothetical sludge ponds, I hope this gives a little bit more practical examples of the importance of detailed numerical modeling and how this can be used to identify risk to any sensitive receptors. That's it from me in terms of the content. I'm happy to take any questions of discussion, and we've got some of the inverter specialists on the call, and as I mentioned, they might be able to jump in if there's any questions that I cannot answer.
Thank you very much, Andrew. Andrew, I'm just going to, thank you, Rochelle. I'm just going to present quickly, just for the CPD points, if you can just remember this word so that we can.
This conference will now be recorded.
Okay, there is a question, Andrew, in the chat. Andrew, are you there?
I am, sorry.
Okay, cool. No problem. So a question just says, very interesting modeling. Has anything been practically implemented and tested?
Well, I guess I might need a bit more explanation on that question. Anything being practically implemented in terms of the city's production wells and injection wells, or in terms of any remediation methods or mechanisms?
Kirsten, do you want to just unmute yourself and give us a bit more detail?
Yes, thanks. Andrew, what I was meaning was, have you done any drilling of wells and pumping and recharge and seen whether your modelling is effective? Not necessarily in the case studies you gave, which I understand were theoretical, but just in terms of your flows and the recharges.
Yeah, we've got our groundwater modeling specialist on the call, but as a background, what we've done is the city has actually installed all of the, well, the majority of the production wells as well as injection wells, and Umberto has been involved in supervising the drilling and testing, both in terms of flow rates as well as groundwater levels as well as water quality for a network of hundreds of wells at the Cape Flats. And that data is continually used to update and validate the modeling. And so the model is a kind of fluid process, if I can avoid the use of a pun there, where we really iterate the process and we update the modeling as we get more detail from each of those locations. So as we encounter different geologies or different flow conditions, we then update the modeling accordingly. So what it did was that allowed us in those examples to have the most up-to-date modeling that is the most representative of the conditions at the time.
Thanks, Andrew. Does that answer your question, Kirsten?
Thanks, Kirsten. I do see another question by Andrea regarding geochemistry modeling to predict the influences of the injected fluids on the groundwater quality. As far as I know, we haven't specifically done any geochemistry modeling itself, but we have done modeling using conservative traces, which would serve as a proxy to look at travel from injection wells to production wells, taking into account our monitoring wells as well. So we do take that into account through conservative traces, but we haven't gone into any detail in terms of modeling any of the specific geochemistry. Obviously, with the monitoring that we've done at the hundreds of wells, we've got a now very robust data set of all the geochemical parameters, mostly taken on a quarterly basis for all of those wells over the last 3 years or so. And so then we use that to validate the modeling as well.
Okay, there's another question in the chat from Lars. Did the model account for gradual degradation of infiltration wells, water quantities?
Oh, right. Thanks, Lars. Yeah, I think if I understand the question correctly, one of the situations we had at some of the wells at our allied scheme, this is not the only scheme that we're managing. We've got the Atlantis as well as the Table Mountain schemes, which we also manage. And at Atlantis specifically, because of the age of the wells, there was some biofouling where we picked up reduced rates over time as the biofouling inducing bacteria produced reduced flow rates. And so as far as I can tell, that was taken into account to some degree, but through our modeling and through our planning, we're hoping to avoid any significant drops in water quantities abstracted from the wells by incorporating a suitable groundwater management scheme. The problem with Atlantis was that the wells were sometimes over abstracted, which allowed oxygenated water to fluctuate into the wells. They weren't run at optimum rates. At the Cape Flat Aquifer, we, as well as the Atlantis Aquifer in our new wells, we've actually put in operating procedures so that the water does not drop below a certain threshold. That's for the reasons for biofouling, but also because of the Philippi horticultural area and the importance. We cannot drop that water level below a certain threshold when we're pumping or injecting by increasing the levels. That would cause flooding. And so we're managing the system very, very closely so that we don't allow that process of biofouling. But obviously, we need to take into account some reduction in quantities coming from the wells over time.
Thank you. Lars, does that answer your question? Oh, thanks. Okay. Okay, any further questions from anyone? I don't see any further questions, Andrew. I found that extremely interesting, and thank you very much for your time. And if you have any questions, I assume, Andrew, can they email you directly?
They can indeed.
Okay.
Either get a hold of us on Umvoto, our website,
yep.
or amanzi@umvoto.com. So that's amanzi@umvoto.com. I'll put it into the chat.
Thank you very much. Thanks, Andrew, and thanks for your time. Thanks, everybody, for your time. And see you at Sustrum. Bye.